we're going to answer a few basic questions in regards to an electromagnetic wave. This electromagnetic wave has the electric field oscillating along the y direction. It has no z component, no x component. So the y component of the electric field in the electromagnetic wave is the amplitude of 100 volts per meter. It could also be 100 newtons per coulomb, and it varies sinusoidally with argument kx minus omega t. So first question we want to answer, what are k and omega? What units are they measured in? So k is termed the wave number. It is 2 pi over the wavelength, and its measurement is going to be in radians per meter. And on a note to ourselves, lambda, the wavelength, has to be bigger than 0, so k can't be negative. And k is only going to go to 0 when lambda goes to infinity. Omega is our old friend, the angular frequency, and that is 2 pi times the frequency. Its unit of measure is going to be in radians per second, and again, since the frequency can't be negative, the smallest omega can be 0. So they're both positive. All right. So let's give k a particular value. Let k be 2 radians per meter. We want to find what direction is the wave propagating in. What we want to note is that this argument for time can only go forward. So out of this argument in the sine function, omega t becomes larger in the future, because omega is positive and t gets bigger in the future. So minus omega t becomes smaller in the future. So in our electromagnetic wave, there's going to be a point where this phase argument is a function of x and t. It's kx minus omega t is 0. And now where is that point going to be in the future? So minus omega t is going to get smaller. For this to still equal 0, kx is going to have to get bigger. So this point where the phase is equal to 0 is going to have to move to the right. And to the right, meaning larger values of the coordinate x. All right, so far We have a k. We know that this wave is moving to the right. The next thing we want to address is what is the value of omega for this wave. So not stated in the statement of the problem, but we're going to assume we're in vacuum. In a vacuum, the ratio omega to k, we expand that out, that's 2 pi f lambda over 2 pi. It's going to give us just lambda f. We know that that is the speed of light in a vacuum, c. Okay. So omega over k, angular frequency over wave number is going to be the speed of light. And if it wasn't in a vacuum, it would be the speed of light in that medium. So we can find omega as kc. So that's 2 radians per meter, speed of light, 3 times 10 to the 8th meters per second. Meters cancel out. So we have an angular frequency of 6 times 10 to the 8th radians per second. And I'm using radians for omega and k to try to remind us that this is an angular frequency and this is a wave number. So they have those factors of 2 pi in them. But of course, a radian per second is the same thing as a hertz. A radian per meter is the same thing as an inverse meter, because radian is itself a dimensionless unit. All right, the next thing we need to find is what is the magnetic field that goes along with this electric field. So we're going to do that in a couple parts. The first is just working out the magnitude of the magnetic field. We know that anywhere in an electromagnetic wave, E and B, their values are coupled together as E is equal to C times B, or E is C times bigger than B. So to find magnetic field strength, we take our 100 volts per meter and divide by the speed of light. So 100 volts per meter over 3 times 10 to the 8th meters per second. It's going to give us 3.3 times 10 to the minus 7. And the units are going to look a little funky here. We'll work it out. I'm going to have volt second per meter squared. So just sort of meditate on that for a second. A volt second per meter squared. A volt is a joule per coulomb, so that's a Newton times a meter over a coulomb. Then I still have a second per meter squared. So that is a Newton per meter per amp, which is in fact a Tesla. So, as desired, B is going to have units of Tesla. 3.3 times 10 to the minus 7 Tesla. All right. Now let's think about what direction the magnetic field is going to point. So let me draw on a coordinate axis, the right-handed coordinate system. So there's the x direction, y direction, and the z direction. And we know that the electric field is pointing along the y direction. And we found that the electromagnetic wave is propagating along the x direction. So there's the velocity of this electromagnetic wave. Then we know that the direction of propagation is given by E cross B. So E along the y direction crossed into B along the z direction is going to give me a wave propagating along the x direction. So this has to be the direction of the magnetic field. So we write out the components for the magnetic part of this electromagnetic wave. It has no x component, it has no y component, and its z component is a function of x and time. Is going to be given by 3.3 times 10 to the minus 7 Tesla, and has the same argument, kx minus omega t. The electric part of the electromagnetic wave, the magnetic part of the electromagnetic wave have the same wavelength, have the same frequency, and there is no phase offset between them. Alright, there's a couple other things we want to find for this electromagnetic wave. We want to find what is the energy density in electromagnetic fields for this wave. And we would need this average value of the energy density to calculate things like the radiation pressure, the intensity, so forth. So this average energy density in the electromagnetic wave is going to tell us about the rate that energy is transported by the wave, and also the rate that momentum is transported by the wave. Alright, so we're going to do this a few different ways. First part, we're in vacuum. So the average energy density is going to be permittivity of free space times the average value of the electric field squared. And that is going to give us permittivity of free space times the RMS value of the electric field squared. And varying sinusoidally, so the RMS value is the peak value over root 2. So average energy density in the wave, I'm going to have from the RMS value squared, I'm going to pick up the amplitude squared over 2, and then times the permittivity. So this is going to be a half. Permittivity of free space, 8.85 times 10 to the minus 12. That's Coulomb squared per Newton meter squared. And our electromagnetic wave had an electric field with an amplitude of 100 newtons per coulomb squared. And you work out what that is. It'd be 4.43 times 10 to the minus 8. And this will work out to be Newton per meter squared, which for an energy density that would make more sense if we multiply the top and bottom by a meter for the units. So that will give us 4.43 times 10 to the minus 8 joules per meter cubed, because a Newton meter is a joule. All right, just to demonstrate, we could have also used a starting point in terms of the magnetic energy density. So 1 over mu naught and the average value of the magnetic field squared, which is going to give us 1 over mu naught B RMS squared. And again, just like with the electric field, the RMS value of the magnetic field is going to be the amplitude of the magnetic field over root 2. Put in values for that. Average energy density for this wave, but calculated from the magnetic field, we're going to have a half, and the denominator will have mu naught 4 pi times 10 to the minus 7, and that is Tesla meter per amp for the permeability of free space, mu naught, and the magnetic amplitude was that repeating decimal 3.33 times 10 to the minus 7 Tesla squared. And sure enough, we calculate that out. We're again going to have 4.43 times 10 to the minus 8, and this is going to give us Tesla times an amp over a meter. Expand what a Tesla is. The amps cancel out. This is again going to give us units of Newton per meter squared, or just jump ahead, it's going to be joule per meter cubed. So energy density, energy per unit volume. Okay. Now these relationships, like the average energy density in terms of the electric field, or the average energy density in terms of the magnetic field, I'm not pulling these out of thin air. These are coming from manipulations of the more fundamental relationship that the energy density in an electromagnetic wave is coming half carried by the electric field and the other half by the magnetic field. Okay? And we can take this underlying relationship and use the fact that the electric and magnetic fields are not independent of each other. So we know that the electric field squared is going to be c squared times the magnetic field squared, and we know what the speed of light in a vacuum is. So that's b squared over epsilon naught mu naught. So if I substitute this in for electric field here, we can find the energy density in an electromagnetic wave in terms of just the magnetic terms. So I'll have epsilon naught over 2, 1 over epsilon naught mu naught, average value of b squared, plus the term I didn't manipulate yet, another 1 over 2 mu naught, average value of b squared. Permittivity cancels out, and we get 1 over mu naught, average value of b squared. And then from this form, to substitute in what b squared is going to be epsilon naught mu naught e squared. And we could also, if we wish, find the average energy density in an electromagnetic wave in terms of just the electric field. And this is all working because the electric field and the magnetic field in an electromagnetic wave are not independent of each other. Alright, so this gets us the relationship that we started from. energy density in electromagnetic wave, if we want to find it just from the electric field, it's going to be the permittivity of free space times the average value of the square of the electric field. So all of these relationships are equivalent to one another, but the more fundamental one is that half of the energy is carried in the electric field, half of the energy is carried in the magnetic field. But E and B are not independent. So in terms of computation, it's probably easier to just find the average energy density in terms of just the electric field or just the magnetic field.